Hello, cool. All right, yeah, welcome to my talk. First of all, I want to say a big thank you to the organizers. It's great to be back here on stage. It's a fantastic conference, so thank you for having me. Yeah, so I'm Samuel. I work on Google Project Zero, and I've been active in the JS engine security space in one way or another for the last 10 years or so, almost. And so this is kind of an overview talk about what's the state of JS engine security and kind of how did we get here. So here I have collected some kind of random headlines from the internet about browser exploits being caught that were related to JavaScript engine vulnerabilities. You can see some Chrome exploits from this year also, like the lowest one is just like 2 months ago. You can see Firefox here, you can see Safari from 2016, so that was the oldest one I could find. But I'm pretty confident that like even pre-2016 there were exploits for JavaScript engines. Maybe they just didn't make the headlines or something, right? So yeah, we are looking at more than 10 years of JavaScript engine exploitation. And I think that raises some interesting questions, like why are they still so insecure, and maybe like how has the landscape changed, right? Like have the types of bug changed, has the exploitation changed in some way? And so this presentation is kind of my attempt at answering at least some of these questions in some capacity. So what do I have for you? I have basically, I'm going to talk a little bit about why, in my opinion, I think it's hard to make these engines secure. Then I have a bit of an history of JavaScript engine exploitation and security, an overview of current and future defenses, and then finally I have a bit of like what's the state of vulnerability research in these engines in 2025. Cool. So to start with, I want to start with something that's not JavaScript. So here you have kind of a classic C++ memory safety issue. It's some random code I made up, but what it's doing, right, is like it's this method or this function that takes an integer and returns whatever is in an array at that index. This has a relatively simple vulnerability, which is that it takes an integer, and so this is assigned int, and so the bounds check here is wrong, right? So if you give it a negative number, then this bounds check like passes, but it's actually not safe, right? So -1 leads to a memory safety issue. So why am I showing this? So this has been around for, I don't know, 30, 40 years. This type of bug is well understood, like it's a very classic memory unsafety problem. And we kind of know how to deal with that, right? So we have safe languages, we have like Rust or Go that deal with these kinds of problems, or even C++, like Clang compiler, you can add certain safety flags that will also mitigate such issues, right? And so ultimately the way this works is relatively simple. Basically what the compiler does is, like before every such array access, it inserts some explicit bounds check, right? And one that's correct in this case, right? So it does a unsigned comparison. And so this works, right? And so this mitigates the bug. Now, let's look at the same code, but now actually without a bug. So this is the correct version of it, where it takes an unsigned integer. The bounds check now is correct. What happens in this case? Actually very similar at first. So the compiler still inserts the same bounds check by itself. But then later on, it's going to do all of its optimization stuff, right? All of the classic code optimizations that a compiler does. And then it actually realizes, okay, wait, there is no way for this bounds check to ever fail because there is a correct one right before it. And so it actually eliminates this check again, right? And so in this case where the code is actually correct, the memory safety kind of comes for free, right? So that's kind of cool. And so I think that is also a big reason why why these approaches work, because they can be relatively low overhead if the code is like correctly written. Now let's get to JavaScript. So here I have an example for a JavaScript engine bug. Again, some made up code here, but what this does is relatively similar. It has an array it's going to access into that or index into that with a provided like integer, and it multiplies the red value with some other given number, right? Let's take a look at how this code could be, like it's hypothetical, but how this could be handled by an engine. So first off, it's going to be translated to some kind of custom intermediate language by the compiler. Might look like this or might look different. This is kind of just pseudocode, but you can see, right, so the bounce check is there, like these two ifs are the condition, then it does the two-number conversion, it accesses the array and does the multiplication. And here again, you will see that the compiler is going to insert an explicit bounce check because, of course, JavaScript is supposed to be memory safe, right? Supposed to be. So you have this bounce check here, but then it actually does something very, very similar to what we've just seen, because the compiler here might think that, oh, you know, this bounce check is redundant because I have just checked the index right up there, and so it's going to get rid of it. Now the problem is, it made a mistake, because what it didn't realize is there was actually like a effectful operation happening between the bounce check and like the existing bounce check and the new one. And so this two-number operation can trigger side effects, and specifically it could run arbitrary JavaScript code. And so an attacker could exploit this in a way something similar to this here, right? So you could pass in some random object as the second parameter, and this object could resize the array when it's converted to a number. So that's the value of function will be called when two-number conversion happens. And so this callback could resize the array to 0, and then we have a problem, right? Because the compiler has just gotten rid of the bounce check, so we're gonna like index at index 42 into an array of size 0, right? And so that's not gonna work. So yeah, same kind of very similar story, right? So we did these compile optimizations. We had the bounce check there at the start, but then we incorrectly removed it later on. So I guess what I'm wanting to say here is I made this diagram. It's kind of sketchy, but maybe it gets the point across. What I want to say is that like typical applications are different from JavaScript engines, right? So if you think about a typical application, and that might be, you know, an image parser, for example, that's written in C or C++. In that application, what you have is the incoming data, so maybe the image data, that is attacker controlled. Then you have the code, that would be the image parser, that is not attacker controlled, but that is direct attack surface, right? So that's where the bugs would be. And then you have the compiler and the hardware, compiler runtime and hardware, and those are kind of one level removed, and that's where we can guarantee memory safety with Rust or whatever. If you look at how a JavaScript engine would look like, I think the picture would be a little different. It would look kind of like this, where actually the data and the code are attacker controlled, right? So that's the JavaScript code. So the attacker supplies JavaScript code, the attacker supplies like the objects or whatever that this code operates on. And now the compiler and runtime, they are the direct attack surface. And so I think this is really what makes it really hard to try and guarantee memory safety at this layer, because that is exactly where the attack surface is, right? I guess put another way, I'm fairly sure that you would find bugs in like the Rust compiler or the Go compiler that would lead to unsafe code, but they don't really matter that much, right? Because, well, your Go or Rust code isn't attacker controlled. And it's quite unlikely that like a normal, like human-written, non-attacker controlled code would happen to trigger one of these bugs in such a way that then attacker-controlled data actually ends up corrupting memory, right? And so for JavaScript engines, the picture is very different. Right, so that was kind of my attempt at explaining why JavaScript engines are a bit unique. Now what I have is a bit of a history, like how JavaScript engine bugs and exploits have evolved over time or maybe changed. For that, I need to start with a bit of an architecture overview of what does a modern JS engine look like. What I have here is the architecture of the V8 engine specifically, but it's not too different from like WebKit's or Firefox's engine. Like they are, roughly speaking, very, very similar. On kind of the top side, the blue parts. You have the JavaScript pipeline, so that starts from JavaScript source code, that goes into the parser, which is going to produce some custom bytecode. That bytecode is consumed by the interpreter, so Ignition in the case of V8. And then at that point, we have a bunch of optimizing compilers that are, making ever faster code. And so those get involved when the engine realizes that this piece of JavaScript code is very heavily used, right? And then it gets optimized more and more. And so there's a baseline JIT that kicks in pretty quickly. And then there's these two optimizing JITs, maglev and turboshaft or turbofan. Those kick in when the code, is invoked like many hundreds or even thousands of times. Then it gets optimized. At the bottom, we have the WebAssembly pipeline. So WebAssembly, that's a new kind of like assembly language for the web that allows compiling Java or existing Java, C++, whatever code bases to run in the browser in WebAssembly. And so that is like a different language input, so it needs a different pipeline. It kind of doesn't really have a parser because it's already like bytecode-ish. So it's like maybe the equivalent would be like the validator, which makes sure that this code is well-formed. And then it also gets like compiled to machine code and executed. Then we have the garbage collector, so the leftmost green block, which makes sure that like dead objects get collected. So JavaScript needs garbage collection, WebAssembly 2 now. So this is the thing that takes care of like freeing unused objects. And then finally we have the runtime environment, which I guess is just kind of a catch-all phrase for everything that's not in one of the other boxes, right? So that's kind of the glue that keeps everything together. It's like built-in functions like array methods that you have in your standard environment. It's helper functions to trigger JIT compilation. It's like code stubs that interact with the garbage collector, that like allocate objects, all of this stuff. This is all kind of bundled in the runtime environment block. So it's a pretty big block here. Right. So back to the history of JS Engine bugs. This is, I think, quite subjective. So this is kind of my view of things. But I would split it into kind of three different phases that we've seen. So the first phase was like kind of pre-2017 was the main phase, I would say. So these, by now I would call these kind of classic JS Engine runtime bugs. Yeah, so they were kind of in this green box. And I'll talk more about them on the next slide. Then maybe around 2017, 2018, things started to shift a bit more to like deeper bugs actually in these optimization pipelines, in the optimizing compilers, etc. And I think these are some of the most complex bugs we've seen in software security. So quite some fascinating things. And then phase 3, I would say, started 2 years ago with WebAssembly. So when WebAssembly became really powerful, that's when we started seeing a lot of new, unique bugs in that area. And I think today it's mostly a mix of 2 and 3. These like early phase 1 type of bugs, they still from time to time come back, but they're usually relatively quickly found because, for example, fuzzers these days are quite effective at finding them. Right, so let's go into these in a little more detail, starting with phase 1. So here I have in red, I've marked the relevant part of the engine that we're looking at. So I think these, you could kind of now consider them classic JS Engine bugs. A very typical bug pattern was what we've just seen, right? This unexpected callback that happened and that would resize something or change some state where the engine didn't expect some side effects to happen, right? And so this was a very typical bug pattern, but we also had kind of more classic types of bug like integer overflows or something like that. I think these bugs were often somewhat local to a single function, right? So meaning all you would have to do to find these bugs would be to look at like one function, kind of read it carefully, and see if it made any of these mistakes. And I think it's maybe not super surprising that these were like the first bugs that were found, because like I guess if you want to like back then start vulnerability research, like one of the first things you might look into where like all of these runtime functions, all of these built-ins, right? So array.push, like in this example, or array.slice. And so then you would like read all of these implementations, and then you would start finding these types of bugs. And yeah, as I said, like they have mostly disappeared from the major engines, I would say. Right, so phase 2, all of these optimization bugs. So here, like this covers basically all of the upper part of my diagram, but the focus is on the like later stage optimizing compilers. Like that's where the complexity lies, and so that's where more of these bugs are found. I think, again, this is a bit subjective, but I think this kind of started around 2017. I remember some really cool pwn2own bugs from that time that I think were kind of the first in this area that were, like, in retrospect, relatively simple bounce check elimination bugs, right? So again, very similar to what we've seen at the start, or like maybe where you know, the compiler didn't realize that a bounce check was actually signed and a negative number would pass to it, or like these sort of things. But then it gradually became more and more complex. Like it involved more and more different parts, different optimizations. And I think also more recently I would put parser bugs into the picture, because we've seen some very interesting bugs in the JavaScript parsers in like optimization that are performed very, very early on already during parsing. So I would put them kind of in the same bucket. I made this slide 3 years ago, which kind of tries to show like a subset of optimizations performed by a modern compiler and how bugs in those can lead to memory unsafety, right? So you have like bounce check elimination on the top right, and so there it's kind of obvious, well, if that goes wrong, yeah, like that's going to be memory unsafety. But there's also lots of other stuff. There's like loop invariant code motion, which can lead to type or spatial memory safety. There's like all sorts of things. I'm not going to discuss this in too much detail. Like this is from a talk I gave together with Amy 3 years ago. So if you're more interested in that, go check out the talk. But I guess the thing I want to say here is that it's not like there's this one bug pattern that happens again and again. It's more like every optimization kind of has its own types of bugs, and like it's really a big, wild mix of issues. Right, and then finally, the WebAssembly bugs. So WebAssembly, it was came around like in 2017, so it's actually been around for quite some time. But the big difference is back then, WebAssembly was really simple. So it was like what would now be called linear memory WebAssembly. So all you had was like one big memory array in some sense, right? And your WebAssembly code, all it could do is like simple loads and stores, arithmetic, logic operations, and then like jumps and calls, right? And so it was a very simple instruction set and a very simple memory model. And it basically just allowed compiling C and C++ code, right? Because you didn't have any sort of object model, there was no garbage collection, or anything like that, right? So that was really a big restriction. And so the major change came with wasmgc, which is kind of an innocent name, but it's really like a massive upgrade in complexity, because wasmgc basically introduced a whole new type system, a whole new object system, and garbage collection support to WebAssembly. And this, like, I don't know, like 5x the complexity or something. I'm just making numbers up, but it was a massive increase in engine complexity. And so this has led to a whole new group of bugs, basically. I tried to find some examples, and this is the bug I found that I think is like the easiest to explain without spending 15 minutes or 20 minutes talking about WebAssembly internals. So this bug, and there were like a few of these similar ones. Pre-WebAssembly GC, in V8 you had this relatively simple object hierarchy that would start at heap object, so that's any V8 object in V8's heap. Then you had JS receiver, which is a heap object, and JS receiver is basically any type of object you can have in JavaScript, and like anything you can perform like property accesses on and so on. That's a JS receiver. And then JS receiver, there were two kinds. You had a JS object. This is like the normal kind, so a plain object, an array buffer, JS arrays, like all these normal JS objects. They are all JS object subclasses. And you had JS proxy, which was a bit special, which let users like configure the behavior, right? And so you could say, if a property is accessed, like run this piece of JavaScript code and so on, right? So this was pre-WASM-GC. And then you had quite a few places throughout the engines that kind of look like this code on the left. It's not exactly like this. Like if you look at this bug, the code is actually much more subtle, but it ultimately boils down to the same code pattern, which is that you had a heap object, right? And you wanted to do something with it, and you would check, okay, is it a JS receiver? And if no, like, well, I don't know, you would just give up and go down some slow paths or whatever. Similarly, you would check if it's a JS proxy, and if it is, then you also would have to run some special handling code, right? Because you would have to run callbacks, et cetera, et cetera. But if it was a JS receiver and not a proxy, then you could be confident, okay, it's going to be a JS object, so I can just cast this object and then do JS object operations on it, right? And so then WASM-GC happened, and basically what it ended up, one of the many, many things it did was it added this new JS receiver subtype, which is WASM object, right? Because it's, like as I said, WASM-GC added this object model. And so it unfortunately, these objects are exposed to JS, but they're kind of weird. But they are still JS receivers, right? And so by doing that, all of the existing code that had these code patterns became unsafe, right? Because now, as you can see, right, like if you pass a WASM object, if you get WASM object into this code, then it's going to pass the first two checks and then do an invalid typecast, and then you end up with type confusion bugs. And I think this is a very typical bug pattern that we see in these engines, where it's not really the new code that is buggy itself. It's more that the new code is changing some invariants that other code implicitly or explicitly relies on, and then that other code breaks. And so this is exactly this bug pattern here. Right, so that's my overview of kind of history of JS engine bugs. Next, I want to talk a bit about like what's happening in the defense space, and I have a few examples. I'm going to start with JIT-less mode, or whatever you want to call it. Again, I had this diagram, right, and so the idea here is relatively simple. It's based on the observation that, well, technically, right, like all of these optimizing compilers, they are kind of optional. Right? If you just want to run JS code, it's enough if you just have the interpreter and you disable all of these JITs. So this is like very obvious attack surface reduction. This is always a good thing to do. And as a added benefit, this may allow enabling like additional operating system level mitigations, right? So kind of like enforced write, so execute that like you couldn't ever get RWX pages and these stuff that makes exploits a little simpler. The obvious downside is, I mean, these JITs are there for a reason, right? So you are looking at performance penalty anywhere between 5 and 90%, right? So it can be really dramatic. It can almost not matter at all, right? So if you have like a static web page, well, okay, whatever, it doesn't matter. If you have more complex web apps, like, I don't know, video editing or photo editing software in the browser, then you might be looking at like really dramatic performance decreases to the point where it becomes kind of unusable. Now, you could, of course, do this just for certain sites, right, and let other sites keep running their JITs. The downside there is then you're suddenly relying on like the security of these other like privileged sites to keep your browser safe, right? Because any cross-site scripting bug or anything like that in these privileged sites is gonna lead to like compromises and kind of unlock these JITs for attackers. So it's a bit subtle, but it's not a great trade-off. For Chrome specifically, Chrome has or V8 has the kind of a funny situation that WebAssembly doesn't actually need an interpreter at all. Like it's the reasons are kind of technical, but like JavaScript benefits from having an interpreter because it doesn't have type information, WebAssembly is strictly typed, right? So you have operations that are like int32 add, float 64 add, etc. And so you can directly like JIT compile this code and it becomes fast. And so WASM doesn't need an interpreter, which means if you turn off the JITs, then you cannot run WASM. So that's not super great. There are a few options, right? So you can add a WASM interpreter for this. So this is kind of what Edge did. I'm not a huge fan of it. It basically leads to you adding new attack surface just for this mode. And this is not trivial attack surface. Like a WASM interpreter is a complex piece of software that's going to have security bugs. So like the trade-off doesn't seem super great. Maybe unless you manage to actually write an interpreter in a memory safe language. Like that could be a thing worth doing. But yeah, so I think that's not a super great option. You could disable WASM, and that's what Chrome did early on. Like you just didn't have WASM support, you turned on this more secure mode. Or the alternative, and this is also what Chrome offers now, is you can keep the baseline JITs and just disable the optimizing JITs, right? So just these two on the right side. The underlying hypothesis here being that most of the bugs are actually in the optimizing compilers and not in these baseline compilers, which are fairly simple in comparison. One data point we have is we started this tracking sheet 2 years ago, 2024. It's kind of a like high quality data set for V8 bugs that are known to be exploitable, right? And so this is public, so I'll make the slides public and then this link will work, or if you just search for V8 exploit tracker or so. But yeah, so these are bugs that we know are exploitable. They come from different sources, so we have in the wild exploits are obvious candidates. We have exploit competitions like Pwn2Own, right? So this is a great set of data. There was unfortunately no Pwn2Own bug this year, but last year's spreadsheet had a bunch of them. And then finally we have this V8 CTF thing running where it's basically kind of an additional bug bounty where people can write exploits for known like end-day V8 bugs and get money for that. And those then also feed into this data set, right? So that's kind of where it comes from. And it's interesting to answer a couple of questions, right? So you see here all these different columns where you can see maybe when was the bug introduced, like what's the average lifetime? Is it like, are we seeing more WebAssembly bugs or more JavaScript bugs, right? So here it's kind of mostly JS, but also like a third of them maybe WebAssembly. And then we have these green and red columns where the middle two are basically telling you, would this bug be affected by turning off all compilers, and would it be effective by turning off only the optimizing ones, right? So only like the two latest ones. And this year they are perfectly aligned, right? So basically what this says is there was no bug in the baseline JITs. All of these bugs were either not in any JIT or they were in the optimizing JITs. And I think this seems to roughly check out. So based on this, like I think roughly speaking, 50% of bugs you would eliminate by turning off optimizing compilers, but baseline JITs are really rarely the problem, right? So yeah. Now I think what's worth emphasizing is I've said 50% fewer bugs. That's a different thing than 50% fewer exploits, right? So these things would be the same if you assume that every threat actor literally has like one V8 bug, but I think that's quite an unrealistic assumption, right? So I think 50% fewer bugs is not enough to get to any sort of like secure browser state, and so I think that's not the full solution, but it is of course a useful tool, right? So that's why it's there. Right. So what else do I have? I have memory tagging, which is the cool new stuff. So many of you probably saw the news that Apple just launched MTE-enabled phones. So that's super cool stuff. So great work. Like brief recap what it is. It's a hardware feature for memory safety. The rough idea is what you see on this picture on the right. Like you have these one of 16 keys or tags, whatever you call them, and then both the pointers have these tags and the memory itself has it, right? And then what all the CPU basically does is enforce that the tag of the pointer matches the tag of the memory region that you're accessing. And so, for example, what this can mitigate are like buffer overflows, right? So if you have, at the bottom you see there is the pointer with the green tag, so tag number 6, and that is being accessed out of bounds, so it reaches into the next area, but that has a different tag that is blue. And so this out of bounds access would be caught by the CPU and like abort the process, right? So if you want to learn more about it, there's a bunch of documentation on ARM site or Apple's blog post. What I would say here is that I think it's unlikely that MTE will have much of an effect on like the core JavaScript engine vulnerability landscape. Like most likely elsewhere, right? But I think in JavaScript and WebAssembly, one problem is that these bugs are basically too powerful. So we have a lot of the time we have these super powerful primitives like arbitrary type confusions, where you can confuse kind of any object with any other object, or maybe like a subset of objects with other objects. And so these bugs will definitely allow you to get around MTE, because you can like confuse an object that has a pointer with an object that has an integer, and then you can read the pointer and thereby the tag, and then you can infer tag values and so on. The other type of bug we have is like arbitrary out-of-bound read-writes. So like not these linear ones where you definitely need to access the next memory chunk which has a different tag, but more like bugs that allow you to access at an arbitrary offset, and combining those with maybe like CPU level side channeling to learn tags would probably also be enough to bypass it. On top of that, I think a big problem is that none of these engines really have tag space left, right? So like both SpiderMonkey and JSC, they use like non-boxing where they encode pointers as kind of floating point numbers, and then the top bits need to be a certain pattern. And V8 uses something called pointer compression, where it uses like 32-bit pointers. And so none of these pointers actually have any bits left. So it would need major refactorings to get like regular pointers that you could then put a tag on. And that I think is another blocker for making MTE work. It seems like Apple has come to a similar conclusion. I don't actually know for sure, but they had this diagram on their blog post, and you can see that they have one Safari chain where they say the first 2 steps are memory corruption, but they survive. My guess is that that would be a WebKit, like JavaScript engine bug, and that they concluded, yeah, like these bugs are too powerful, but I don't know for certain. Right, next up I have sandboxing, so that is one thing I've been working on quite a lot for the last few years. This is a bit of a different approach, so here we say, okay, we accept that these bugs will happen. Like ultimately we cannot write bug-free code, and as I've tried to explain before, like if you have these logic bugs in compilers, you end up with memory corruption. So instead the idea here is that we want to limit what memory can be corrupted, and that becomes a new security boundary. So let's kind of construct this from scratch. We start by allocating a bunch of virtual address space in our process. So this is 1 terabyte. This is super cheap. Virtual address space is super cheap on any modern operating system. So then this space is 1 terabyte. This is where all of V8's objects go. All of these heap objects, JS objects, WebAssembly object, everything goes in there. Now what you have is you need to be able to somehow represent references from one object to another. Pre-sandbox, you would have just used a raw pointer, but that's not safe in a sandbox world, because if you have a raw pointer that then gets corrupted, this would allow an attacker to access any other memory outside of the sandbox address space. And so raw pointers are no good. Instead, we use offsets, right? And so in particular, V8 uses mostly uses 32-bit offsets, so that's kind of a nice memory saving. But roughly speaking, yeah, you turn all of these pointers into offsets, and then if the attacker corrupts an offset, that doesn't do them any good, because that offset is limited to 1 terabyte, and so you cannot get out of this sandbox space. Now, of course, there's going to be external objects, so stuff like like blink objects, DOM objects, and so on. So these need to be referenced as well. Again, raw pointer is not safe, and so instead what we do is like a pointer table indirection. So in the sandbox, it stores an index that goes into a table that has type and pointer information, and then this is how you get a safe, like correct reference to a real object of the correct type, right? So this is the basic idea, like ban all of these pointers. The reality looks a little more complicated these days just because there's like different types of external objects and so on. So there's actually multiple of these tables and multiple like external regions, but the rough idea still stands. Maybe briefly, like in the future, I think it would be really cool to get hardware support for this. Currently, it's all software. You could imagine a future where basically, as soon as you run JS or WASM code, the CPU goes into some low privileged mode and actually cannot physically access any non-sandbox memory. Like this would be super cool. This would be very similar to like userland kernel split on like modern operating systems. And so like ideally in the future, you would be able to run completely untrusted machine code, not just JS or WASM, but like untrusted attacker controlled machine code in this mode and be like confident that it works. Yeah, for that, so I think that's what I kind of would say Sandbox is, that's like Sandbox version 2.0, so that is like with hardware support. I guess at that point you would have like two different types of code in a Chrome renderer process. You would have like privileged code that can read and write all of the memory, and that must be careful, like if it operates on untrusted data. Or that code then might actually someday be like memory safe, and then it would work. And then you have sandbox code, and so that's the code that like cannot physically access privileged memory, and this would be all of the JS and WASM code. Like just briefly, like I think this is how I would imagine the split to look like for V8 itself. So as I said, like all of the JIT generated stuff, all of that is sandboxed, like untrusted code. All the interpreters run sandboxed and like kind of helper stubs like inline caches. And then on the other side, binding code, like the glue code to Blink, like to the rest of the browser, that probably needs to be privileged. And then garbage collector and compiler probably would run privileged, just because like those don't really have memory safety bugs themselves. Like the compiler produces unsafe code, but then unsafe code runs sandbox, so that's fine. But the compiler rarely corrupts memory itself, right? So that's probably okay to run it privileged, and it would be quite a pain to try to get it to run in sandboxed mode. So it's probably not quite worth it. And then the split happens somewhere along that, like all of these built-in runtime functions that like transition, for example, to kick off like compilation, or that transition into the rest of the browser code. Right, so maybe a bit of a like progress update. So where are we with this? So we've been working on that for 4 years or something now. I would say we are probably at somewhere like along version 0.95 or so. Like at the bottom you see this progress bar. There's a lot of like uncertainty where it's actually at. I would say most of the design level issues are solved. Like the design is kind of, at least like the version 1.0 design is kind of final now. But there's still a lot of implementation bugs left, right? Not necessarily like in the sandbox itself. It's more like that a lot of the V8 code pre-sandbox was like, the existing V8 code was written without the sandbox attacker model in mind. So a lot of that code actually has to be adjusted to work correctly in the sandbox world. Yeah, it is already part of the VIP, so we are paying like $20,000 for high bypasses, and for hardware support there is a prototype to play with, but there's cooler stuff coming up. I'll have something about that in a minute. Yeah, right, let's go. So again, this diagram is like a little sketchy, but I think maybe you could imagine that sandboxing, what it kind of does is add another layer below the like compiler and runtime that are direct attack surfaces. It adds like this additional layer, and then this is where we can try to actually get like better safety guarantees. And on the other hand, if like hardware is already below that, so if we get hardware sandboxing, that would be super interesting. Next I have, and the final thing I have is like WebKit's JIT cage. This is something that they have on their newer Apple chips. It has a similar idea in spirit, right? In that it wants to somewhat sandbox untrusted code, in particular JIT-generated code. It does have a quite different goal, though. I think that's an important distinction. So what the JIT cage tries to prevent is basically CFI. It wants to get some sort of CFI guarantees of, like, this JIT-generated code cannot do syscalls. It cannot just jump to arbitrary other code. Like, it needs to always go via trampolines. But crucially, the JIT cage does not try to prevent memory accesses to anywhere else, right? So this mitigation kicks in at a much later stage in time. Like when the attacker already has arbitrary read-write, then this thing kicks in while the sandbox exactly tries to prevent the attacker from gaining arbitrary read-write in the first place. But anyway, this is super cool stuff. It relies on like custom, basically CPU features, but it looks like a lot of these CPU features will be available in an upcoming ARM hardware feature for like all of ARM chips, ARM-based chips. That's called POE2, and that should be super cool. Like that's I had a link in the previous slide. Like that's a CPU feature set designed for in-process sandboxing, where this is one subset, but it also allows like taking away memory access and so on. Right, and so I guess as a comparison, again, this is also a bit sketchy because, as I said, JIT cage and sandbox have different goals, so it's kind of hard to compare them. But as I said, like the main difference here is that the JIT cage doesn't try to prevent arbitrary read-write, so it doesn't restrict the accessible memory. But that is the core of the sandbox, right? The main thing that sandbox tries to do is restrict the accessible memory. For the software-only sandbox, like it kind of implicitly also restricts the instruction set in the sense that it assumes that the compiler-generated code cannot be corrupted because it's outside the sandbox, and so it assumes that only like normal instructions are emitted by the compiler, and so it kind of restricts it in that implicit sense. This could be made explicit by adding software code validation, where it validates the JIT code, but I think the real interesting stuff is the hardware sandboxing, which would have all of these features combined. Yeah. So that would be interesting to see if it gets to that point. Yeah, so summary, I think in my opinion, the sandbox is a useful mitigation in itself. Like I guess mitigation is a bit of an overloaded term, but in the sense that it already now requires attackers to have multiple bugs, right? And so the core V8 bug, and then an additional sandbox bug that could get fixed anytime. There is a caveat, and we'll see some examples later. Like there are certain bugs that can directly bypass the software-only sandbox, like right away. But those are somewhat rare. But I think, in my opinion, the cooler thing actually is that the sandbox is more of an architecture, like a different architecture that enables powerful mitigations itself, right? So this would actually make it possible to use memory-safe languages in something like V8 and get a benefit from it, because you would use the memory-safe languages for the privileged code, and then that code is actually like not, like that reduces the attack surface because bugs in that code are less relevant then. And similarly, you would, in the privileged code, you would benefit from hardened C++ or even MTE, right? And then on the other hand, the sandbox code would benefit from things like hardware sandboxing, what I just said, or software code validation to also categorically mitigate certain bugs. So I think that's a plausible path towards actually getting, at some point, a secure and high-performance JS engine. Yeah, I guess what I would say now is that, like, if you're starting today to build a new JS engine or any kind of engine that runs untrusted code, like I would strongly suggest start with like an architecture like this from the start. Trying to retroactively fit that onto an existing engine is a huge pain. Like there's so many things that like need to be redesigned to make this work. So starting with that from scratch would have been so much nicer, but yeah, 15 years ago or 20 years ago, this what couldn't have been envisioned, I guess. Right, and that brings me to the final chapter here. What does vulnerability research look like today? I think like the kind of the classics are still going strong, right? So we have manual code auditing, like manually reading code, like hypothesizing about potential bugs, like figuring out the interesting attack surface, where the cool bugs would be, and then looking for them. There are some really awesome bugs by Song Jung that you can like. I think this will link to like the Chrome bug tracker where you can see a lot of them. So these are really like high quality bug reports for really powerful bugs. So I suggest checking those out. And then there's of course also fuzzing, right? So that's still going strong. This can find really cool bugs, kind of unique bugs that a human would probably not find just because like a human thing's kind of structured and fuzzers may just like generate random stuff. It definitely also finds less cool bugs, but that's just how it is. And I guess the like promising thing to try here is like very targeted fuzzing, right? So fuzzing like specific components, fuzzing for variants of previous bugs, like that sort of approach. But I think the main new thing this year is that we're starting to see like AI-powered approaches finding bugs, and so in particular Big Sleep, which I was also working on a bit this year, and like taking care of like the JavaScript integration, and so this has been quite successful. Like I think up to date we've reported 11 vulnerabilities, although there's one low impact, so let's make it 10. But 10 bugs, and there are some really cool ones in there that were found by this system. The way it works is relatively simple in my opinion. Like it's actually more simple than what we've seen in the previous talk. It is basically just like a modern like reasoning model, like the ones you've seen solve like these math Olympia problems or so on. Like it turns out these are actually pretty good at understanding code, and then you give these models the tools they need. So in particular, like a code browser, so it can read the source code, like find cross-references and so on. You give them the environment, so the JavaScript engine shell, and then you kind of point them somewhere and say, like, go find a bug and write me a test case. And so this works surprisingly well, and I expect that we will see more such systems reporting bugs, and more, like also in Big Sleep, more bugs should be found. Right, so I have now some examples, and I will actually start with 2 bugs that were found by Big Sleep this year. The first one is a bug in the bytecode compiler of V8. The test case is actually quite simple. It's what you see at the bottom right here. It has to do with like weird new JavaScript features that are like this await using syntax, which is very new. The bug is kind of fun. It's basically, I'll try to explain very quickly. So you have, in JS, you have generator and like async functions, and these are functions that basically need to be able to resume, right? So they can yield at a certain point, yield back to the caller, but then they need to be able to resume from that same point later on. The way this is implemented is really simple. Basically, the function is just compiled as a normal function that has a big switch case at the start. And then there's an associated generator object that has the like switch case, right? And so this function just does a big switch and then jumps to the current like point where it should resume. And the way this is implemented is in 2 phases. So the parser is going to kind of try to compute how many of these cases do we need. And then the compiler builds the switch table based on that. And this bug, what happened here was that there was a mismatch where the parser counted maybe 5 of these points, but the compiler actually wrote 6, wrote 6 cases into the switch block, and then it kind of corrupted the bytecode, and it led to like arbitrary bytecode execution, which turned out to be a super highly exploitable exploit primitive. So super cool bug. What's maybe interesting is that this bug, it looks simple. It looks like fuzzers should have found it quickly, and I agree that like they should have. The problem is all of the fuzzers that were running at this time that didn't understand this syntax. They knew about await using, but they didn't know it could be put into a loop. And so they couldn't have possibly generated this test case because they didn't know this syntax. Yeah, I have another one. This is also a Bixby bug. This is a bit similar. It's also related to bytecode corruption. On the right side, I have an example of bytecode where it uses like a try-catch statement. And you can see the way this gets compiled is basically at the bottom you have this table that just says if there's an exception between like bytecode at offset 3 and at offset 6, then jump to offset 6. This is all it says. Now the fun thing is that the bytecode, the maximum bytecode size is 512 megabytes, but the offset is actually stored as a 28-bit integer. So it can only represent integer numbers up to like 256 megabytes. And so, well, if you make a bytecode that's really large, put a try-catch around it, then it ends up truncating this offset, and again it jumps into the middle of bytecode, and you get a very similar primitive. Again, really cool bug. Again, hard to discover by like generic fuzzers, just because it takes quite some time to build this long bytecode. So most fuzzers would time out way before they got anywhere close. Yeah, and then I have the final one. This is a bug found by the V8 team last year. This is super cool. This is a like bad interaction between web audio, which is a browser component for like manipulating audio as it like gets output, and the JavaScript engine. And basically what happened is that web audio lets you use custom JavaScript processing nodes to modify audio, like raw audio. And also web audio, for performance reason, it kind of changes how the CPU handles floats. We'll get to that in a second. But the gist then is that the JS code in this web audio module, it runs in an unexpected CPU mode, and that turns out to be exploitable. And so I think that's a really cool bug. It also affected other browsers. So Safari also assigned, or like Apple assigned a CVE for Safari for the same bug. And I would say quite possibly this is my favorite bug of the last few years. I need to get into a bit of a background on floats. So kind of getting back to like basic computer science, floating point numbers, right? So you have maybe 32-bit floats, and then you divide them, like you usually take one sign bit, and you then take X mantissa bits and Y exponent bits, and then the float value is like this formula you have here, so the sign bit times kind of the mantissa, and then to the power of exponent, roughly speaking, right? And so the mantissa is like what gives you precision, and the exponent gives you like the range. Now, normal float numbers, they have this property that the mantissa does not have any leading zero. So to the first bit in the mantissa will be a 1. And I guess the reason here simply is that if it had a 0, then like instead you could just adjust the exponent to represent the same number. I think that's the idea. And so, however, there are then a certain number of like denormal or subnormal or whatever numbers that are exactly that, where the mantissa starts with leading zeros. And since like as I said, like since you can adjust the exponent to represent these other numbers, the denormal numbers are only really unique around 0, like really, really small numbers around 0. That's where the denormal numbers like come into play, right? And so for some reason that's something I also personally don't fully understand, but it seems to be the case that in the CPU you can disable handling of these denormals, and then they just become 0, and that leads to significant performance improvements on floating point operations. And so that's why web audio wants to disable them, but the JavaScript spec says basically that, well, denormals should be supported, like they are not 0, right? So they need to be there. And so the proof of concept for this bug, it is fairly simple. It looks like this. You have a denormal number outside a web audio module, and then if you print it, you get this number, right? Like it's a very small number, but it gets printed. It's not 0. But if you look at the same value inside one of these audio processing nodes, so that's the audio processing code, then it suddenly becomes 0, right? And so like you observe this, and it happens because the CPU now is in the special mode where denormal numbers are ignored. Right, and so it turns out that this is actually exploitable. Like, this is super fun. You can go to the URL here to see the full commented exploit, but the short version is that, like, really all this exploits is that the compiler at some point makes the assumption that a denormal number is not 0, right? Which normally should be fine according to the spec. And you see this in the like 5th line or so in the function where we ask, like, is denormal 0, like object.isDenormal 0, and so the compiler there will later on during its optimization will say, no, I know that denormal is like not 0, so this must be 1, right? And then at runtime this is actually true, right? So the compiler thinks it should be false, but at runtime it's actually true, and then you take this number and you like do other integer operations on it, so you get you expand the confusion, right? The compiler is confused about a Boolean. You expand this to get the compiler to be confused about integer values, and then from there you get memory corruption because it like ends up kind of out of bounds accessing an array. Yeah, again, there's a fully commented proof of concept exploit at this URL, so if that sounds interesting to you, take a look.
Right, and that's all I have.
Thank you very much, and happy to take questions.
Thank you, Samuel, for those insightful updates. Always a pleasure to see Project Zero continuing to set the standard for vulnerability research. Do we have any questions? Feel free to raise your hand, please.
Thanks for a great talk. When you spoke about the sandboxes and hardware measures how to do that, I thought about the virtualization itself, because JavaScript is the code and data together. So what do you think about using virtualization for such sandboxing?
I mean, yeah, it is being done, or it has been done, right? There was I think, Microsoft Edge mode where you could run tabs in a virtual machine. I guess my suspicion would be that overhead-wise, it's much more heavyweight than what we are doing, right? So the V8 sandbox is like a 1%-ish overhead, so it's super low overhead. I suspect with any virtualization, you would be looking at much higher overhead numbers because you have to get much more heavyweight infrastructure behind, like spinning up virtual machines and like spinning up kernels in these machines or whatever you need. So I think that's the main limiting factor. But otherwise, it could be a very strong boundary for sure.
Thanks.
Do we have more questions? Okay. Thank you, Samuel. Please give huge round of applause for Samuel once again.
Thank you.